yes, I'm happy to start.
So we're happy to have Nathanael Berestycki from University of Vienna for our second talk today, and he will tell us about dimers and imaginary geometry.
Right. Well, thank you very much for the invitation to give a talk, and thank you everyone for being here. So I want to report on a series of works that we started some years ago with Benoît Lallier, now in Paris, and Gaurav Ray, now in Victoria. So this work started when they were both with me at Cambridge. And so this will be about the dimer model. I will be brief about what is a dimer model, because we've just heard Martin's great talk with this introduction in particular. But just to remind everyone, so we've got some finite bipartite graph, planar, and a dimer configuration is just a set of edges which cover every vertex exactly once. So you can think of it as a perfect matching on the graph. And a dimer model for me will just be you pick one of those dimer configurations uniformly at random. Of course, you could assign edge weights if you liked, but let's not do that. And what you can see from a picture like this is that it's if you do it on a square lattice, then that's really the same thing as domino tiling, because you can think that every dimer edge, you're gluing together two adjacent squares. That gives you a 2x1 rectangle or a domino. And if you do the same game on, let's say, the honeycomb lattice, this is the dimer model on the honeycomb lattice, then if you kind of think what is the equivalent tiling picture that you get, then really a dimer edge corresponds to gluing together two adjacent equilateral triangle, and that gives you a rhombus or losange. And so altogether, this would be the same as a losange or rhombus tiling on the right. That's equivalent to that. And as Martin pointed out, I think he used the exact same picture actually. So you can immediately see with your naked eye that this defines for you a height function. And somehow the main question in the dimer model concerns the study of this height function. So this height function was defined by Thurston. It's the main observable, and it allows us to think of the dimer model as a model for random surface. Good. So it's a very classical model of statistical mechanics. I don't need to convince you of this, probably. It was introduced in the 60s by Castellane, Temporalis, Fisher, and there's been really an explosion of work since the 90s, led in particular by the really remarkable work of Rick Kenyon, and also later in collaboration with Okunkov and Sheffield and many other people that I couldn't write on the slide. And a key aspect of the dimer model, we've heard some of that in the previous talk, is the fact that it's exactly solvable. And so as Martin said, somehow the starting point for basically all of these works is to exploit the fact that you can compute things in the dimer model in terms of determinants. That's a remarkable fact. And another aspect of this exact solvability is that it has incarnations, this model, in other models of statistical mechanics, including random tilings. I've basically explained that. But also strong connections with the 6-vertex models, Ising model. And for me, what's going to be important in this talk is a connection to uniform spanning trees. And yeah, so the main difficulty of the model, as we heard in the previous talk, is the fact that somehow the model is highly sensitive to boundary conditions. So even in the last talk, we heard if you just modify the weight, if you just modify the boundary conditions in one row on the boundary, it's enough to completely change the scaling limit of the model. And that's something that may be surprising, somehow surprising to us when we're more used to the fact that in statistical mechanics, somehow the exact detail of the boundary conditions So long as you specify something that is macroscopically meaningful, then you're going to get one scaling limit, and somehow the exact detail is not so important. So what I want to report on is a program that we started with Benoît Lallier and Gaurav Ray, as I said, where we try to step away somehow from the exact solvability of the model and try to devise methods that will allow us to prove universality insofar as it's possible. So as I said, the model is very sensitive to boundary conditions, and that suggests that proving universality for the model, universality of fluctuations, universality of the behavior of the model somehow is going to be a difficult problem. And what I'm going to try and explain is kind of a set of tools really that we've developed. I think it's probably today one of the most versatile methods to try and obtain convergence for the height functions in the dimer model to their scaling limit. This result applies in several setups, but there's one governing principle. And what we will see is that at least in the case of simply connected regions, there's a connection to what's called imaginary geometry. And what is imaginary geometry? Really, it's a fancy name maybe, but at the heart, what it means is it's just a coupling between a Gaussian free field and some SLE curves in such a way that the Gaussian free field at every point kind of measures the winding of SLE, so in some suitable sense. And what we will see is that this coupling between imaginary geometry and, between Gaussian free field and SLE, in a sense, is just a continuum form of Temporalis projection. So I'm not expecting anyone to be familiar with any of these terms. So I will try to explain what I mean. But that's just to give you a flavor of the approach that we take. We are replacing exact properties, exact computation in discrete that exploit the determinantal structure with some symmetries that take place at the continuum level somehow. That's the idea. So so far we've managed to implement this idea in some setups. It's very, very far from over. So the understanding of dimer model, to have a general theory of scaling limit for height functions that is truly robust to boundary conditions, it's still very far. It's still a very long way away, I would say. But we've had some success in implementing this idea, nevertheless. So there's, in the case of simply connected regions, we obtain a result which covers several actually situations, including the case of isoradial graphs, so Temperleyan or flat boundary conditions, which I'm not really going to describe. Likewise, the case where the height function on the boundary is linear is something that we can handle. There's a certain kind of balanced random environment that is covered by this result. We've started thinking about how to implement this result or this method in the case of Riemann surfaces. So we have a first paper that is already on the archive, and we're finishing a second. Together, they will really say something about the case of Riemann surfaces. I'll hope to say a few words about this at the end of the talk. And there is also some work that is in preparation with Levi Haunschmidt, who is a student here in Vienna, PhD student of Fabio Toninelli. So this covers, this says something about an off-critical dimer model, but I'm not going to talk about that. So in that sense, because this kind of method covers a bunch of situations, I think of this as quite a robust way to approach scaling limits for the dimer model. And I'll try to say something about what this method is. So the starting point of this method is something called the Temporalis Projection, which really is a really beautiful and remarkable bijection, which was known, of course, since the work of Temporal in the 1960s, but perhaps was not exploited to its full power until relatively recently. And the idea is to relate the Daimler model to a spanning tree, uniform spanning tree. And to be precise, what we can do is we can start with the uniform spanning tree on a graph gamma, which will be simply connected and planar. That's important. And what we will do is be able to associate a Daimler model on a modified graph, G. And G will consist of the graph gamma, the original graph gamma, the dual graph, and we superpose them in a way that I will explain later. And when we do that, so as I said, this Temporalis projection, it has a remarkable property. One is that it exchanged the model of uniform spanning tree on gamma for the model of the Daimler model on this superposition graph G. And the remarkable thing is that if you're interested in the height function on the graph G for the Daimler model, then you can compute it in terms of the winding of branches in the spanning tree. So if you're interested somehow in the height difference between this point and this point on the spanning tree, then you're just going to find a branch that connects these 2 points and computes the winding of this branch, by which I mean just number of left turns minus number of right turns. Yes, and then there's some normalization, factors of pi, which this is a bit a matter of convention, really. And so the kind of message from this bijection is that, which is really what we're going to exploit, is that if you're interested in studying the scaling limit of the height function for the Daimler model, then you can replace this question by the question of studying the winding of branches in a uniform spanning tree. So it's a very nice idea, this Temporalis projection. I thought I will explain briefly what it looks like. How do you make this projection? How do you start from a spanning tree on the graph and associate a Daimler configuration on the superposition graph? I won't explain the relation between the height function and the winding of branches, because that takes a bit more work and we don't really have the time for it. But so the way we start is as follows. So we're going to start with a graph gamma. So this is the graph gamma here, and so this graph has vertices and edges, of course. It also has faces because this is a planar graph. And we're going to construct the superposition graph G, so which, as I said, consists not only of the original graph gamma, but also of its dual. So we add a vertex for each face of gamma, and we also add intermediate vertices, or I don't know how they are called, these white vertices here. We add one for each edge of gamma here, and in between two faces, we draw an edges that go through this middle vertex in this manner. So the superposition graph consists not only of the original vertices of gamma, those of the dual gamma dagger, but also this extra new vertices, one in the middle of every edge, and we just join. We just add edges in this manner, connecting a face to the neighboring edges and to the neighboring white vertices of these edges. So that's the superposition graph G. And what I'm going to show you is how to maybe start from a Daimler superposition graph and tell you how to obtain really a pair of dual uniform spanning trees on gamma and gamma dual. So this is what we've got here, dimer configuration on this superposition graph. So you see that every vertex is connected to a unique dimer. So maybe there's some extra dimer that we, no, sorry, there's an extra dimer here that we don't see. And so how we're going to find a pair of spanning trees on gamma and gamma dual. So what I'm going to do, first of all, I'm going to orient each dimer from black to white. And so maybe I didn't say it very clearly, but the graph G is a bipartite graph. It has a black and white coloring in such a way that each edge connects two vertices of different colors. And the way this coloring is done is simply that these new vertices that you added, you call them white. So in the middle of every edge, you've got a white vertex and everybody else is a black vertex. And so we can orient dimers from black to white. We can do that whether a dimer lives on an edge that was originally primal or originally dual, like this one. And then what I can do once I have done this orientation, so I have these dimers, I can think of them as being little arrows. And what I'm going to do now is just double each of these dimer edges. So I just interpret a dimer edge as the first half of an edge that now connects black to black. Like there was a dimer here, and instead of this dimer, I now have this doubled edge, and it goes from black to black. So I've done it here on the primal graph, but I can also do it on the dual graph. And when I do it on the dual graph, this is what I get. These edges from black to black. And also on the dual graph. So there was a dimer here, and it's been replaced by this double-edged, and likewise, this is what we get. And yeah, what I claim is that once we've done that, we've got a pair of subgraphs on gamma and gamma dual, which is oriented. So these subgraphs have the property that the edges, they come with an orientation. And what we see is that these subgraphs, they are self-dual to one another. So you cannot have one edge like that and one edge like that. They cannot cross. And simply because this would, if you had both this edge and this edge, then it would mean that this vertex would be connected to more than one dimer. So that's just not possible. And so these subgraphs, they are self-dual to one another. And moreover, every vertex has exactly one outgoing edge corresponding to the unique dimer attached to it, basically. And what you can see is that, so I'm not talking about boundary conditions. Let's imagine we're living in a plane for now. And what you can see is that this means these trees, these subgraphs, they actually must form self-dual spanning trees. And the reason for that is that, yeah?
You seem to have shown that they're forests rather than trees. I mean, I don't see that you get connectedness necessarily.
Right. So yeah. So a full proof would require a bit more arguments, perhaps. In fact, when we're really so in fact they can really deforest depending. I mean, it's a question of boundary conditions basically. So they're spanning trees in the sense that they're wired. If you wire the boundary, then they really become trees. So okay, it's a detail that I would prefer not to think too much about. But what you can see is that it's just not possible to have a cycle because if there was a cycle in one of those like that, then somehow there's the dual guy inside, and the dual guy cannot come out. So so this means also the dual must form a cycle. And at some point, this picture keeps going and keeps going, but at some point it has to stop, and that's just not possible, because out of every vertex there is really an outgoing edge.
So this is where you really need the topology, yes?
Say again?
This is where you need the topology. You're using the Jordan curve.
Yeah, that's right. Yeah, exactly. So yeah, thank you very much. So it's very important that we are here in the simply connected region. So that's fundamental. Thank you very much for saying that. That will be relevant for what I'm going to say later. And so we have this this operation, this temporary bijection is a local operation. If I see a piece of dimer configuration, I can tell you what the trees look like near this piece somehow. But somehow, yes, once you think of it globally, then what you've got is a pair of self-dual spanning trees on gamma and its dual. Oh, so that's just the bijection. By the way, why is it a bijection? It's also obvious. If I see this configuration, how do I get the dimer configuration? So the point is that I will just simply take the first half of each edge, basically, and that will give me the dimers. So it really is a bijection. So what I'm not saying here is in particular why is it the case that there's a connection between the winding of the branches of this tree and the value of the height function for the dimer. But okay, we cannot do everything in the talk. As I said, once you've got this wonderful bijection, you're asking yourself, what is the scaling limit of the winding of branches in a uniform spanning tree? So let me state a general theorem, which is why I think this method applies in a bunch of situations. So I'm going to start with a uniform spanning tree living in the domain D. Delta, you can think of this as being some kind of measure of mesh size, but the graphs, they don't have to be the square lattice. It can be, we're going to have just some sequence of graph G delta. So that's what's in the theorem here. And so that's G delta, the sequence of graph. You can think of delta as being something like a mesh size, but it's just some number. And associated to this sequence of graph G delta, we can consider a uniform spanning tree and take H delta, the associated winding of branch. So here I really mean that if you look at the height difference between point X and the point Y, I just find a branch in the spanning tree that connects these two points. I can go via the boundary if needs be, and I just compute the winding of the branch connecting X to Y. So just number of left turns minus number of right turns, and of course, if the edges are not straight, then I have to account for the winding of these edges as well. So the theorem says that if you so there's some assumption which I will tell you in a second what they are, and then under this assumption, as delta tends to 0, the theorem says that you look at the winding and you subtract the expectation, then this converges to a multiple of the Gaussian free field. This multiple, I write it in the form of 1 over chi, and chi is 1 over square root 2. This isn't quite the same constant as showed up in Marchin's theorem for a couple of reasons. One of them is that basically there are normalization as issues associated with the green function and therefore the Gaussian free field, and also normalization issues associated with the definition of the height function. So for me, yeah, so for me, sort of, it's measured in units of 2 pi rather than in units of numbers of dimers. But modulo these normalizations, it is really the same constant as you saw in Marchin's talk an hour ago. So that is what the theorem claims. Let me just tell you what these assumptions are. I think the assumptions are very general. Really, the main one is that this sequence of graph, if you do simple random walk on this graph, then it will converge to Brownian motion. So these graphs, they are embedded in the plane. And the main assumption says that if you do random walk on this graph, then up to a time change, it will converge to Brownian motion as delta tends to 0. And the second condition is a kind of crossing condition that says that if you've got a rectangle of fixed aspect ratio, then if you start somewhere here, then there's a positive probability that random walk will go from this ball to that ball without leaving the rectangle. So this is what we call the uniform crossing condition, and it plays a similar role to the Rousseau-Simon-Welch assumption or estimating percolation. For me, I take it as an assumption. And finally, the third estimate, which the third assumption, which is technical, says that simply in any given region of space, then the overall density of vertices it's bounded. So yeah, so you don't, there's not too much overcrowding of vertices, and also the edges. Remember, the edges, they don't have to be straight, but I require them to have bounded winding, so they cannot wind around infinitely often. So yeah, so I think that makes the assumptions basically as general as one can hope. Roughly speaking, okay, maybe this one here is more for convenience than is really needed. And what you can see, so I'll show you again the theorem with now that you know what the assumptions are, and it tells you that the winding of uniform spanning tree, they will converge once you remove the expectation, converges without scaling to a multiple of the Gaussian free field. Now, it's a bit funny to write the constant as 1 over chi when chi is 1 over square root 2, but there is a reason why I do that, and it will have something to do with imaginary geometry. So this constant chi has something to do with imaginary geometry, and that's why we phrase it this way. One thing to point out is that it's really fundamental that you remove the expectation. Without that, then there's no way, even if you assume simple random walk converge to Brownian motion, there's no reason why the expected winding should be anything nice. But it really is the winding minus its expectation that converges to a Gaussian free field. That's very important. Are there any questions so far? Okay.
So just to make sure, yeah. So the theorem that you presented, there must have been some version of it before as well, maybe in a specific case, or this is your theorem, right? But
yes, that's right.
Where it was known or something.
So
like that.
Because convergence of the height function in the Daimer model was known in certain specific situations, for instance, Kenyon's work on the Daimer model showed convergence of the height function to the Gaussian free field. And because this Temporalis projection was known, then as a corollary, you would also get it in this particular situation where Rick's result applies.
Okay,
I think if I'm not mistaken,
it was never described in such a way as the winding of branches, though.
I think, if I'm not mistaken, Itai was the first to conjecture that in this form. And I don't know the story whether he conjectured it because of connection with the Daimer model or independently. So I would have to ask him that.
Oh, okay. Thanks a lot.
Yeah, so, but in this form, certainly in this form, this is our result. And I think what is interesting about this result is the fact that we're not making too many assumptions about the graphs. It's not a result of exact computation that gives us this result.
Definitely. Yeah. Thank you.
So let me tell you how we prove this result. And I hope that the connection with imaginary geometry will be apparent from that. So the idea is to say, well, we've got the uniform spanning tree and we know a lot about the uniform spanning tree. So the idea is to say, well, the first thing we want to ask is what is the scaling limit of the uniform spanning tree itself? And because there's this Wilson's algorithm somehow in the background that is a wonderful way of describing the uniform spanning tree. We know that branches of the uniform spanning tree, they correspond to loop arrays random walks, and loop arrays random walks converge in the scaling limits to SLE2 curves. So if you put together what this says, then if you combine this result of Lawler, Schramm, and Werner, a very famous result, and Schramm's original SLE paper, as well as really using Wilson's algorithm, then this says that if you're looking at the uniform spanning tree on the domain on the domain with a approximated by a square lattice with a very fine mesh size delta, then this uniform spanning tree will converge in a suitable sense. So I'm not telling you the sense in which it converges. That was part of Odette's work. To an object which we may call the continuum uniform spanning tree. And the branches of this continuum tree, they are given by SLE2 curves. And what will be especially relevant for me is this version of this result, which is due to Ariel Yadin and Amir Yehudayov around 2010, where they proved that actually this convergence is true more generally. You don't need to be on a square lattice. You only need to assume that simple random walk converge to Brownian motion. So the uniform crossing assumption is not needed for this. It's just convergence of random walk to Brownian motion that is needed. And so this will be relevant. So we've got, so we're in a good situation. We're interested in the winding of the uniform spanning tree, and this tree converges in a suitable sense to a limiting object, the continuum uniform spanning tree. So, once you see it this way, it's kind of obvious what you want to do. You start with a uniform spanning tree, and I've just told you, if you apply these results, there is a convergence to the continuum uniform spanning tree. Now, we're interested in the winding of this tree because by Temporalis projection, that gives us the discrete height function we're interested in. So, first thing you want to do is to try to say, well, given this continuum uniform spanning tree, can I give a meaning to the notion of winding of branches of this uniform spanning tree? And if I can somehow I make this diagram commute, right? This is this arrow here is what I'm really interested in. That is what we know. And what we've got to make sense of is these two other arrows. So you can think of it in this manner. So really there's this part one where you try to define the winding of a continuum uniform spanning tree, and there's a part two where you try to make this diagram commute. But for presentation, it will be somehow more easy to try and tell you how do you make the diagram commute, basically. So and it's only, or more precisely, I will tell you how to assign a notion of winding to a continuum uniform spanning tree, but I won't tell you immediately that this winding is given by a multiple of the Gaussian free field. So that comes later, somehow the identification of the limits. So how do you make sense of winding when you've got a rough object where the curves, instead of being discrete paths going from a point x to y, where you can make sense of number of left turns minus number of right turns, how do you make sense of the winding when this path is instead a rough object like an SLE curve? And okay, so we need to kind of distinguish. There's two useful notion of windings. If I've got a simple path in the complex plane, then I can talk of the topological winding around Z. So here's Z and here's my curve. Then I can ask myself how many turn around Z has it done. So here, I don't know, 3 pi over 2, something like that. And there is a more interesting notion, more closely connected to what we're interested in, which is this notion of intrinsic winding. So if the path was smooth, what you would do is just look at the turning of the path. So you plot the tangent the path at any given time. So here's my path, maybe it goes between here and here. And at any given time, I can look at the tangent vector gamma prime and look at the argument of that and just integrate this over the entire length of the curve. And that gives me the intrinsic winding. So this is really what corresponds to the number of left turns minus number of right turns. It counts really how much the path winds around, not with respect to an origin Z, but really intrinsically how much does it wind around. And so here's a lemma which is very simple, but I think a nice observation. So probably people are aware of it, but I wasn't. And so what is the lemma? The lemma says that if you've got a simple path, which is smooth, so let's say this is a simplest path, then the intrinsic winding, you can obtain it as the sum of the topological winding around the starting point and the end point. So basically, this is saying the only winding that you can do some winding around the origin. And well, if you try to wind in the middle, then because the path is simple, you're going to have to unwind. And so the only non-trivial thing that happens, it happens either at the beginning or at the end. And so the intrinsic winding, the total winding accumulated by the path, it ends up being equal, really equal to the sum of the topological windings around the start and the end point. That's the only non-trivial winding that you can do for a smooth path. And basically, the point is that if you imagine now that your path is not smooth, but is rather something like an SLE, so nasty fractal path, then somehow this is a very useful observation, because the topological winding is a much better behaved object. So if I have, so let's think of the following situation. I've got here a domain and maybe a point Z here, and I'm trying to, you should think of this as being some kind of the branches of the uniform spanning tree, so an SLE2 curve going to the point Z. If I'm interested in the kind of topological winding of this path around the point Z, that's here, well, there will be some stuff that's happening locally around Z, but somehow all the fractality of the path is in itself not that relevant. So what matters is just how much this path is going to wind around Z, and that's basically a well-behaved object. So I want to say that if I have kind of a path that is converging towards a continuum path in a suitable sense, then the topological winding is, except for what's happening at the very end of this path, basically well behaved. And the consequence is that if I have a discrete tree that is converging towards a continuum tree, then the winding of this tree is almost a continuous function of this tree. So of course, all of the work is in the almost, but that's kind of the philosophy of the approach that we're taking, that if you've got uniform spanning tree converging, then so does the winding. So okay, that's the basic idea in our approach, if you like. And if you want to really prove the results we're interested in, then you've got to also identify the limit, not just say, well, the height function converges to a scaling limit, which is this kind of abstractly defined winding of the continuum uniform spanning tree. And this is where it's useful to have this connection with imaginary geometry. So this is quite a technical subject. So if I want to have time to say more stuff, then I cannot really go into full details. But the slogan of imaginary geometry is that it gives us a coupling between Gaussian free field and SLE curves. in such a way that if I start with an SLE kappa curve, then I can interpret the SLE kappa curve as what's called the flow line of the Gaussian free field, provided that you divide it by a certain constant chi. And you need a certain relation between chi and kappa to be true. So this is the relation that is required. And for us, you can check that what will be relevant will be the value kappa is equal to 2. And you can check that when you plug in kappa is equal to 2, then you get 1 over root 2 here for chi. So what is the meaning of this slogan? Really, it says the following. It says that there is a coupling between a Gaussian free field H and an SLE kappa curve eta, such that if I condition on the values of the SLE curve, so if I condition on the particular realization of the SLE curve, then the value of the Gaussian free field in the complement is just given by a Gaussian free field where the boundary values are obtained by, so minus lambda. Lambda is a certain constant whose value you should ignore. You should pretend lambda is equal to 0. And the boundary conditions are minus lambda plus chi times the argument of G prime. So what is G prime? G prime is the map that makes the curve swallowed into the real line. So just that removes the curve. Okay, so the tip eta t, I should call it. This is eta t here, and it's mapped to xi t, and so this here is going to be the image of the entire curve. So we have this conformal map that removes the curve, and what I'm saying is that given the curve, then the value of the Gaussian free field is just a Gaussian free field in the complement of the curve, where the boundary values are given by basically chi times the argument of the conformal map, of the derivative of the conformal map, G prime. And I mean, this is a kind of technical statement, but if you think about what does the conformal map do, then the conformal map, if there's a lot of winding somehow in your curve, if your curve suddenly starts doing a lot of winding, then somehow the conformal map, when it removes the curve, it has to unwind the curve. And so this GT here is basically related, you know, this argument of G prime T basically gives us the winding of the curve. So this is another interpretation, another way that you might try to define the winding of a path is through conformal maps. And in that case, your definition would be argument of G prime T. And so what we're saying here is that in this imaginary geometry coupling, there's a coupling between the Gaussian free field and an SLE curve, such that given the curve, the value of the field H on the curve is basically given by chi times the argument of G prime. In other words, the values of H divided by chi on the curve, they correspond to the winding of the SLE. And if you like, you can view this as a continuum form of Temporalis projection. So this connection is not just true with one SLE curve. It's possible to really couple not just a Gaussian free field with a single SLE curve, but with a whole bunch of SLE curves, and these curves correspond exactly to the continuum uniform spanning tree. And this is at the end how we identify the limit as being 1 over chi times the Gaussian free field with Dirichlet boundary condition. Okay, so it's as I said, it's a bit of a mouthful, it's a bit complicated. I want to spend a couple of minutes to say something about our results in the context of Riemann surfaces. I don't know how much time I've got. Does anybody know?
I also don't know exactly, but I think you can go on certainly for another 5 minutes and perhaps.
Okay, that's all I need.
All right.
So I will have a surface. I will start with some surface. So you can think maybe this is the torus. And I have a graph embedded on this surface, so gamma. And again, what I will do is consider the dimer model on the graph G, which is obtained by superposing gamma and its dual. And there's a bit of Euler's formula that you need to do to realize that if you just try to define the dimer model like that, it's in general not going to work. You have to do a bit of surgery. You have to remove a certain number of edges. And in general, the number of edges you have to remove is given by that. So that you get really a bipartite graph when you do it. And then it turns out when you have that, then you have really a graph on which it's possible that has dimer configurations. So it's dimerable. There's maybe an interesting analogy you can make with geometry, which is that if you're on a surface, if you're given a surface and you try to put a flat metric on it, so a metric with no curvature, then you can only do it if this number is 0, and likewise, and if this number is non-zero, then what you have to do is introduce a certain number of conical singularities. So, okay, it's a bit of geometry, which maybe it's not relevant, but there is an analogy which is quite nice. And so we remove the correct number of edges, and this really corresponds to creating puncture in the surface in some sense. And so really analogous to these conical singularities. And once you do that, it turns out really that you have a graph that is dimerable. So you can study the dimer model on this graph, and it makes sense to do that. And you can ask yourself, what can you say about the scaling limit? Now, as I've tried to explain, our whole idea is to kind of think about Temporalis bijection and try to establish a scaling limit for what you get out of Temporalis bijection, because at the end of the day, the height function is expressed in terms of winding of the tree. But okay, so here it's not going to be a tree, and so we've got this surface, but Temporalis bijection is local, so it doesn't care. It doesn't care at all. If I give you just a piece of dimer configuration, I can define, I can see what it corresponds to in terms of subgraphs on gamma and its dual. And it's still going to give me a pair of self-dual subgraphs, but now this is not going to be tree. So as was observed in one of the questions we had, if the surface is not simply connected, then in general it won't be a tree, but we will get some object. And we call that Temperalian forest. And as you can see from this picture, in general, this Temperalian forest really can have a cycle. So this is on an annulus. I don't know how well you can see it on the screen, probably a little bit. And what we're able to prove is we're able to describe this Temperalian forest sufficiently well that we can prove this Temperalian forest, they have a scaling limit. And the scaling limit is universal, so it does not depend on the details of the graph, so long as this assumption star is satisfied. So basically, that's again convergence of random walk on the surface to Brownian motion. And this limit is conformally invariant as well. So if you have a map between conformal map between two Riemann surfaces, then the limiting Temperalian forest is really the same. And the corollary is that if you look at, there is a notion of height function on these surfaces as well. And the dimer height function has a scaling limit which is universal, does not depend on the details of the graphs, and is conformally invariant. In the case of the torus or the annulus, the surface is sufficiently simple that exact computations become possible. And in that case, the limit is known and was described before that in a paper of Julien Dubeda. It's called the compactified Gaussian free field. And so in particular, these results, they solve a conjecture that he made. So I will stop here and thank you for your attention.
Thank you. Any questions?
Hi. I just wanted to clarify a small point. When you were talking about taking dimer tilings on the Riemann surface, you said that you have to remove certain edges.
Yes.
So you can remove arbitrary edges, or there are some well-chosen edges that have to be removed. What exactly?
Right. So it can be, yeah, thank you for asking that. What you have to remove, what you have to remove is, it can be anywhere on the surface. You choose where you want to remove it. What you have to remove is something like that. So, here maybe this is a primal face, and here we've got our white vertices like that. And what you have to remove is a whole edge. So meaning you have to remove something like that. Okay, so it's there was an edge here, an original edge here with a white vertex, and it's really the white vertex that I've removed, and I've removed also the edge that went.
So it is actually like puncturing the plane, as you said.
It really is the same as a puncture, and yes, exactly. Maybe one thing that I should point out, and you can see where the torus and the annulus is a bit simpler already here, is that if it is the torus or the annulus, so in the torus, then G is a genus, it's equal to 1, B is 0, so 2 minus 2 is 0, so there's nothing to remove. On the torus, likewise on an annulus, there is nothing to remove, and you can just study the dimer model without creating any puncture. And in that case, you get the compactified Gaussian free field. Right. So that's what the result says.
So can I also ask? You mentioned the height function for SLE2, like this continuous height function for SLE2. If I change kappa, what would this height function correspond to in a discrete case?
So is there, okay, so this is kind of a reverse engineering question you're asking.
Yeah.
Can I interpret, yeah, so there is actually an answer to this. So one can, it's part of a big conjecture. So so there is this notion of interacting dimer model. So at the moment, what we have done is assign, we've given each dimer receives a weight equal to 1, but you can modify the model and consider an interacting dimer where, for instance, on the square lattice. Also, if you see this, well, maybe this was a bit too big. So let's do it in this color. If you see this dimer and this dimer in parallel next to one another, you will also give it a weight. So you favor configurations in which two dimers are parallel to one another if they're neighbors. So this is a way of adding interaction to the model, basically. So when you do that, you change the models very substantially. So all the tools, basically, they break down. The model is no longer integrable. But there's been this absolutely remarkable breakthrough by Giuliani, Mastropietro, and Toninelli in the last few years, where they're able to prove that, nevertheless, if it's a perturbative approach, so if the weight of such a plaquette is very small, it's very close to 1, sorry, then the height function will converge to a Gaussian free field, but with a different variance. And what this means is that if you were to apply Temporalis projection to this interacting dimer model, you'll get a tree, but this tree will not be a uniform spanning tree. And the branches of this uniform spanning tree, they will converge to SLE, but SLE with a different variance. And how is the variance? SLE with different kappa, and kappa is related to the different variance through the relation of SLE of imaginary geometry. So basically, if you want to see SLE with different kappas, then you've got to change the model to make the dimers interacting, and then apply temporalis projection. And the branches of this tree, they should converge, but I mean, nobody's got an idea for how to do that. They should converge to SLE kappa, where kappa and the variance of the Gaussian free field, they are related via imaginary geometry. Does that make sense? I don't know if that answers your question.
Thank you very much. That's perfect.
Nathanael, I also had a question. So you said that you have the general result that you mostly need that the random walk converges to Brownian motion, and also this analogy with Russo-Simmer-Welsh. I remember a recent work of Asaf Nachmias, Ori Gurel-Gurevich, and Daniel Jerison. They spoke about orthodiagonal embeddings and double circle packings, and proved that random walks converge to Brownian motion. So I get the feeling that that's a very general setup. So does your result show that the dimer height function converge to the Gaussian free field in this very general geometry?
Right, it depends. I see. So you want to take a discrete, yeah, I haven't thought exactly about that. So it may well be, okay, it may well be. So somehow the exact combinatorics, they matter a great deal here. So I would have to think, presumably if I start with their orthodiagonal maps and superpose the dual to them and look at the dimer model on the resulting graph, then I guess it applies readily. I mean, you would need to check the crossing assumption, but
right.
I think that's not very difficult. In general, yeah, I think it should not be difficult. I think it's actually, it's part of their proof. In fact, they prove something like that. So, so if you just start with their planar map and superpose the dual to them and look at the dimer model on the superposition graph, then yes, I think the result applies. Usually in the realms of planar maps, so I think kind of understanding dimers on random planar maps would be a fascinating story. It's not completely clear what is the right model of planar maps one would like to consider. So you want to consider certain kind of planar maps weighted by the dimer model partition function on it. But it's likely that the combinatorics, the exact model of planar maps you put on, has a high impact on the limiting picture somehow. So this is a reflection of the fact that it's highly sensitive to boundary conditions, for instance.
I see.
Trying to prove something like that and trying to answer this would be really fascinating, and we're, I think, very far from it still.
Okay. I had another question, maybe more tangential slightly. On the hexagonal lattice, if you look at the dimer model, then then that's one of the classical cases that has been studied, and the height function converges to the Gaussian free field. I guess that's Canyon's work.
Well, with the right boundary conditions. So if you make appropriate assumptions.
With the boundary condition, yes, let's do that. And then you can, on the discrete level, somehow, if you take the complement of the dimers, all edges which are not dimers, then that gives you a set of loops, and those are conjecturally going to SLE6. And somehow you can also see them in the discrete level as related to the height function. They are just the boundary of where the height function is even somehow. So you look at the parity of the height function. So this is like e to the I times pi times the height function. So it has maybe something to do with the flow line of a Gaussian free field that should be an SLE6. So is any of that possible to rigorize, that the flow line of a Gaussian free field, but on the discrete level goes to the flow line in the continuum, and then...
I see very much your question. I think there is a huge problem in all of these kind of questions. So you have this basic relation between a Gaussian free field and spiny trees. something like that, which says, here what I've shown is that if the spanning trees converge, then the flow, then the field converge. What you're asking is a reverse question.
Yes.
And you're saying, oh, if the field converge, do the flow lines converge? Unfortunately, this is a much harder question. So, we shouldn't expect really continuity in a suitable sense for a question like that. So, I believe what you're asking is a much harder question. At least, with these techniques, it will be much harder. Somehow, because what I'm exploiting here is the easy direction of this correspondence, if you like, that we know something about the flow lines and we want to deduce something about the field. You want to deduce something about the flow lines knowing something about the field.
Right.
And unfortunately, much harder.
Right. But in suitable situations, you would conjecture that to be correct somehow. I don't know. maybe the question doesn't make sense because maybe the flow line.
It's hard to know how to formulate the question in such a way that it makes sense.
Maybe it doesn't make sense. Maybe in very special situations. Okay.
In very special situation. Yes, exactly.
Yeah. Okay.
Whereas somehow what we've got here, the theorem, I didn't state it like that, but it's quite a really, in some sense, quite a general that says if you've got a scaling limit for the what you get when you apply Temporalis projection, then the height function converges. It doesn't tell you what that limit is, but it tells you that there is convergence.
I see. All right. Very good. Thanks a lot.
You're welcome. Thank you very much all for your attention and your questions.
Let's thank Nathanael again. See you all next week.
Thank you.
Nathanael?
Yes?
Yeah. I had an unrelated question, but since it's the end of the seminar, maybe it's okay. If I wanted to teach something about this, so suppose I wanted to show that the dimer height function converges to